Welcome and hello. This is a video exercise in RIMS, and in this exercise, we're going to be dealing with reservoir guide curve. So what that means is we have a reservoir and a guide curve. We're going to try to keep the storage of water in the reservoir at that guide curve. All right, so what I have on the screen here is my RIMS. Before we get started, I'm going to put up a model schematic. Very simple. It's just inflow into a reservoir, the reservoir itself, and then node 1 and node 2. There's a channel connecting node 1 and 2, and then a demand D2 at this node 2. We can consider that like an in-stream flow demand. All right, well, let's go ahead and get started. I'm going to right-click New Project. This is the New Project dialog box. Click on Next for New Project. I'm going to give it a name, which is E6 for Exercise 6, Reservoir Guide Curve. And then uncheck this checkbox. And in here, I want to paste in the directory path for my project. Okay, right here is the directory. So I'm just going to copy that path, Control C to my clipboard for you Windows users, and then Control V to paste. That looks good. And then click Finish. All right, so right here is my project. There's nothing there yet. So let's create a launch file, right click, and come down here to Run As, Run Configuration. Then in this left panel here, click on Russell/RIMS2 application, and then click on a new configuration button here at the top. All right, I'm going to name this configuration the same thing as the project, Reservoir Guide Curve. We can skip some of these fields. We need to provide a main Russell file path. This is going to be a relative path to a file that doesn't even exist yet, but we'll create it in just a moment. And then the paths to the three DSS files. dvar file means decision variable. I'm going to put that in a DSS directory, dv.dss. Same thing with the state variable for svar, sv.dss, and then dss init.dss for the initialization file. Okay, down here for part A, I'm just going to be generic and call it project, state, and init for part A, and then part F in the sv file, the init file. All right, and then the time step, what I'm going to do is go with the 1 month time step. That's the default. And this is going to be a 10-year simulation. So the start date is 1921 on October. So the end date will be 1931, which is right here in September, because the water year, it begins in October. All right, so that's good for the main tab. In the configuration tab, select that and then click this checkbox checked on for Russell Plus. And then in the far right tab here for common, click on shared, click on browse, and then select our project E6. Okay, so that's done. Click apply. We can close that dialog box. And if we expand our reservoir project, we now have the launch file right here. It's kind of a long name, but here it is, launch at the end. Okay, so I'm going to just move that back. Next, what I'm going to do is set up my directory structure. So this right here is my project on my local drive. We already have these two files created down here, which is the launch file and the .project file. Now I'm going to create these files and folders. So a DSS directory with those three files that we already referenced in the configuration, and then a run directory with a few files right here. All right, and here is the project directory. So I'm just going to right click, new folder, DSS. Oops, got the caps locks on again. DSS, okay. I'm going to drill into the DSS folder and then go new. Text document is fine, dv.dss, and then delete the .txt on the end. All right, so that's ready to go. If you hold down Control, you can just drag, and then it'll give you a new file. F2 to rename SV, that's good. And then one more time for the init file. All right, so we're set up for the DSS directory. One more directory, this is going to be the run directory, run. Okay, and then inside the run directory, we've got main file, a main Russell file. So new text document main.wresl. Okay, that's good. And then I have a directory called system. So new directory system. Okay, inside system, I've got a few more Russell files to create, just blank files. All right, so I've set those up, just all blank files ready to go. We're going to edit these files and add the content in just a moment. Before we do that, let's start by adding the data to the DSS file. So if I go back up to the project, DSS, we have these three files right here. There's nothing to do for decision variables, but for initialization, we need to specify the initial starting storage for the reservoir. And then for the state variable file, that's where we're going to provide data for the inflow time series data set and a demand time series data set. So to open up DSS view, I'm going to go File and then open up those files. Here is the project directory, DSS, and then init.dss. Okay. And then one more time, Control O and sv.dss, open. Okay. Okay, I'm going to select init.dss and then go up to data, manual time series. And then for the path, I'm just going to paste in what I have prepared. So project res1, this refers to the storage in reservoir 1. Part C is storage. The units are going to be in total acre feet, so TAF. I'm going to start in October 19. I'm sorry, this is the look back. So I'm going to start a few months before the actual start of the simulation. I'm going to just start in July, and that's will be 1921, and then the start time 2400 hours. Okay, so down below here, I'm just going to type in 50 a few times. Oops, the type is period average. Okay, type in 50. So 50 and 50, that's good. This is September, which means the next month is going to be the beginning of the simulation. So that's fine. I'm only going to be looking back 1 month, but just for good measure, I added a few extra months as well. All right, so I'm going to go save there, and then, it's probably worth mentioning that for part F, it says init right here. This is consistent with what we typed in the configuration file. The same way when we go over to the state variable.dss file, sb.dss, and then go to data manual time series. Now I'm going to input the inflow data to the reservoir. So if I just paste in what I have prepared here for the path and then hit tab, this part F is state. Remember state, that was also in the configuration file as part F for the state variables. So that's how you make the connection between the part F, B, and C. Now I'm going to start at the beginning of the simulation for the start time here. It's going to be October of 1921 at the end of the last day. The units will be in CFS because we're talking about inflow now. Now I went ahead and just synthesized my own data for inflow and demand. And it's a whole spreadsheet and it's not terribly complicated. But I'm going to go ahead and just paste in the numbers I have. So I'm going to copy them from Excel and then come back over here to DSS view and click on paste. Okay, try that again, paste, there we go. I'm a little concerned the type isn't coming in right here. Let me change it to period average. And I'm just going to type it in here, period AVER, and save. Let's see if that takes. Okay, let me just double check to see if that is correct. Okay, cool. So that showed up. I'll display the inflow and the demand in just a moment. Let's create the demand. I'm going to go up to data, manual time series. You know the drill. Let's go ahead and paste in the path name or the path name parts. This is D2. It's in flow, and then it's also going to be in CFS. So let's type in 31 of October, 1921. The start will be 2400 hours. The units will be in CFS, and then the type is going to be period average. Okay. Back to Excel, this is where I have some demand data as well. We can consider this demand, maybe it's in-stream flow, maybe it's for urban use or agricultural use. Doesn't matter really. Just wanted to add some extra data to make the exercise interesting. So let's click on save. Let's go ahead and view this data now. All right, so up at top, the red, this is the inflow, and then the demand downstream is in green. So you can tell already that there's plenty of supply, there's plenty of water to satisfy this demand, and it's a 10-year time series. So we have 120 data points, which is 10 years at a 1-month interval. Okay, so let's go ahead and actually open up the files now that are in this run directory and then populate them. So starting with the main.russell file, that is right here, and then Control O to open up the files here in the system directory and open. I reordered the files here. I'm going to start with inflows right here. I'm going to be pasting in the code and just kind of explaining it because it takes me too long to type and record and everything. What this is we're identifying the inflow to reservoir 1. The part C is flow. The units are CFS. This is a time series. Next file over is the demands. This should look similar in format, except now the variable is D_2. Again, flow and CFS. All right, the next file over is channels. We only have one channel. and it is channel 1, 2. Now this C12 represents the total channel flow, and then that's composed of the sum of two parts. I'm breaking this down into a C12 min and C12 extra, where C12 min is going to be the demand, the minimum flow, which will be rewarded with a multiplier in the weights file, in the objective file. So we'll get to that in just a little bit. If there's any flow in this channel that exceeds the minimum flow, that demand, that will be considered extra flow. So after we run the model, we'll take a look at these three paths and the results over the 10-year simulation and be able to identify that relationship, how minimum plus extra equals the total. The next file over here is reservoir data. So what we have at the top is a decision variable, which represents the actual storage of water in the reservoir. And then below that is a state variable. This is the capacity of the reservoir, and it is set to 100,000 acre feet. All right, the next file over is the constraints, which utilizes this keyword goal. The first constraint here is reservoir continuity, which basically says inflow into the reservoir minus the outflow out of the reservoir equals the change in storage of the reservoir, where this -1 here represents the storage in the previous time step. That's why we had to have that one path in the init.dss file representing storage. And then after that, we have reservoir capacity. This basically says that the storage in the reservoir cannot exceed the maximum, which we set to 100,000 acre feet. Okay, the next one down, I need to change the label. This is the continuity in arc C12 or channel C12. So basically the total equals the sum of the minimum and the extra. That's where this is enforced. This is a hard constraint. And then lastly is the demand, which basically says that the minimum value cannot exceed the demand. This D2 is the demand that we assigned in our demands file and is linked to that time series data set. Okay, so that's the constraints. We've got two more files to populate. Here's one of them. This is the objectives file. What we're going to do is set a positive coefficient associated with the flow in channel C12 min, which basically means that our only objective in the simulation is to satisfy that downstream flow requirement. And then the last file is the main Russell file. This is what calls all the other files. So we have one cycle. The model's called base. It's first, it's the only one there is. And then we're including all of these files in the same order that I defined them. Because sometimes you may get an error when running the model that says you're using a variable before it's been defined. And for me, I reduce the chance of that happening if I build my model in this particular order. So I'm going to save all those files. Let's go ahead and run the model. So I'm going to go back to RIMS and we'll see what happens here. Right click on the launch file, run as, and then click on the launch. Okay, so that looks successful. I'm going to go back to DSS view. Now I'm going to open up the db.dss file. This is where our results were written to. Right here is the storage of water in the reservoir for the 10-year simulation. And that's hilarious. So what happened was the reservoir started half full at 50,000 acre feet. And then it just emptied all the water at what looks like the first opportunity. And then it's completely empty for the entire 10 years. All right. Now that is optimal. I'll tell you right now that is optimal because remember, our only objective here was to satisfy the downstream flow requirements. This right here, these three paths represent the flow through C12. Here's a plot of it. And excluding this first time step or two where all the water's draining out, I'm just going to zoom in on this area right down here. Okay, so this green line here represents the downstream demand. That's the C12 min. If we add that to the extra, which is red, we get the total, the sum here, which is in blue. It may be a little easier to see if I zoom in. Okay, so that's a little easier. This is the downstream flow, the minimum demand. This is the extra, and then this is the total. Okay, going back to our reservoir storage plot, this has got to be bothering someone besides me. What I want to do is create a guide curve for this reservoir and set it at a constant 50,000 acre feet so that the water remains constant in the reservoir for the entire year at half capacity and it's not down here at 0. So let's go ahead and do that, run the model, and then let's actually get a little bit more complicated with things. I'm going to bring up the reservoirs file, which is right here. And then at the bottom, I'm going to give myself some space and then paste in this right here. What we're doing is defining a new state variable, simple state variable, T underscore res1, which is the target. So that has a value of 50. The total capacity up here remains at 100, but we want to aim to keep the volume right here at 50. And how we're going to do that is come over here to the constraints, give us some new lines down towards the bottom of the file, and then paste in this constraint right here, which aims to penalize reservoirs off the target storage. So this constraint is called target underscore res1. We define the left-hand side and right-hand side as the storage and the target, and if there's any deviation, we're going to impose a penalty. I set the value up to 5. I purposely made it less than what we set for the objective right here of 20, meaning that satisfying the downstream flow requirement is more important than maintaining that 50,000 acre feet guide curve. All right, so let's go ahead and save everything here and then run the model. I'm going to go right click on the launch file, run as. So that's ran, and then let's take a look at the results. I'm going to go to db.dss, view, refresh the catalog. Okay, so let's check out the reservoir storage over the course of that 10-year simulation. Looks like we nailed it. We're right at 50,000 acre feet for the entire simulation. And because that was a soft constraint, we have this slack and surplus variables popped up. Looks like there's no violation whatsoever. So that's good to see, which means our objective function value is the exact same as what it was in the previous run, except this time our reservoir is not empty for the entire time. However, this is pretty boring, just stuck at 50, and also fairly unrealistic. So next, what I want to do in this exercise is to create a guide curve that changes each month, meaning it's not a constant 50, but rather it starts at 50, and then that changes over the course of the year. So to do that, I'm going to go back to my reservoirs file, which is this one right here. Here we were defining the target for reservoir 1. I'm going to comment that out, and then just below it, paste in a new way to define that target, and that is by looking up the target value from a table called res1 underscore data. This is a table I need to create in my project files. So let's bring up the project directory. It is right here. This is project. This is run. And it looks like a lookup directory was created for me. So that's cool. I'll just go ahead and click on lookup. And I want to create a table called res1 underscore data dot table in this directory and then populate it with the actual target numbers for each month. So to do that, just go ahead and right click, new, create a new file. I'm going to paste in the file name. So there's that. And then let's go ahead and open up that file. I'm going to go ahead and open up the file, run, look up, here it is, and then paste in the contents for that target storage. So the first couple lines of this file are just a comment, so that's not even seen by the WRIMS. And then after that, we have the table name, res1 underscore data, the month, which ranges from 1 up to 12, the target, this is again the target storage in 1,000 acre feet. It starts at 50 because our simulation starts at 50. That makes sense. It goes up to 62.2 and then back down to 50. Now, I could have put this into a time series data set. However, this data repeats year after year, so it makes a little bit more sense to just put into a table like what you see here. All right, so let's go ahead and save that and run the model once again and see what kind of results we have. Run. All right, and then back to our db.dss view, refresh. Let's take a look at the reservoir levels now. Okay, cool. So now we have reservoir levels that fluctuate between 50 and 62 over the course of the year. However, you will notice that it's not the exact same every year. I zoomed in here on the first 3 water years. You can see that the first year it gets all the way up to 62, but then on the second year, water year 1923, the maximum is about 60. So I can scroll across and take a look there. 1925 looks really low. 1926 through 29 all kind of look the same, actually. So that's good. Let's go ahead and see if we have any errors. Highlighted the slack and surplus variables associated with that soft constraint. And if we take a look at the plot, sure enough, we do have some errors. There's some deviation between the storage and the reservoir and the actual target storage. We can quantify these numbers if we go up to Tools Math Functions and then select on the statistics. So the average is 0.44, and remember that's 1,000 acre feet. So 440 acre feet, 441. So that was the average, I'm sorry. And then the maximum is 3.69. So there does happen to be a month with a violation of 3.69 thousand acre feet, meaning the storage in the reservoir is off that much, either above or below. It's kind of hard to tell because we're penalizing both a surplus and a slack by the same amount. In fact, you know what? I'm going to create a new time series data set that I can add to this db.dss file. And what it's going to do is it's going to show that guide curve, because right now it's just pasted in that table, but I don't actually have it in DSS view to compare with anything. So real quick, I'm going to go up to data and then create a new time series data set just for this purpose. It's going to be res1 storage, but there's a preceding t, so this is the same thing as the variable name. I'm not actually going to read this into WRIMS, but I am going to compare it here in DSS view. Okay, I filled out the start date, start time, units, and type. Now, down here for the values, I'm just going to manually type in the numbers that we used from that table, which are right here. So the first month is October. I'll type in 50 for the first value here. Oops. Okay, I moved things over. So let's see how this works. 50. Okay, 50.8, 52.5, 55.1, 56. So that's 12 months. I'm going to go ahead and copy that and just paste it 9 more times below. So that's the first water year 1922, water year 1923. Scroll down, water year 1924. And that's 10 years right there. So I'll click save. No. Let's take a look at those storage values now versus the target. So I have these paths. And let's go ahead and click the plot button. Oh, cool. Now I'm going to zoom in just so I'm looking at 1 or 2 years at a time. All right. So the red line here is the target, and then the green line here is the actual storage. So we can see that we incurred a little bit of violation and hence penalty in this water year 1923. And if I scroll over, it looks like 1924 was a little bit. 1925 has quite a bit, the most so far. 19, 26, 27, 28, 29, 1930. The last year has a little bit right there. I would say the most critical year is 1925 right here. So we could look at the actual numbers, but let's just go ahead and move forward. Next, what I want to do is instead of identifying one single target guide curve elevation, which is one of my pet peeves with ResSim 3.3, is I want to identify a zone, like an optimal zone, not just an optimal value. So I'm going to come back to this data table right here. And instead of having a target value, I'm going to have a target min and a target max. And that's going to have a specific range here, which is 5,000 acre feet. So minimum is 50. That's what it was before. I kept the target. I'm just calling that the minimum now. And then the maximum, I'm just adding 5,000 acre feet. So 50 and 55, 50.8, 55.8, all the way down. So I'm going to save that data. And of course, I need to update some more of my code to work with this change in the table data. I'm going to click on the reservoirs table. And instead of this single value target, which was a constant 50, and then it was a constant value for each month, I'm now going to have a maximum and minimum value. So what you're looking at here is 2 more state variables, t underscore res1 min and t underscore res1 max. And it's going to just reference the target min and the target max from the same file that we were referencing previously. Next, I'm going to go over to the constraints file, which is right here. And this constraint here will not work anymore because this variable doesn't exist. And this was sort of a strict penalty based on a single point. So let's delete that and then paste in the new constraints. So we actually have 2 constraints here. They're both soft constraints. And what we're doing is we are penalizing the reservoir if it happens to be below the minimum, but not above the minimum. And we're also penalizing the reservoir or the objective function value. We're imposing a penalty of 5, once again, if the reservoir is above the maximum. Is that right? Yeah, I think I got it right. Let's go ahead and run the model and see what happens. So save, and then back over to RIMS, then right click and run. Okay, so that finished up. Let's go back to the db.dss file and then refresh. Here is our reservoir volume. So let's check that plot out. Okay, interesting. It's kind of hard to evaluate its performance just by looking at this plot. So let's take a look at the surplus and hold on a second. I can't remember which ones that are left over. I'm going to delete all the paths and just rerun the simulation. So 1 second, right click. Okay, view, and then refresh. So let's take a look at the slack and surplus variables associated with the penalty when the reservoir storage is above the max or below the minimum. All right, so it looks like, yeah, we have the most penalty incurred in 1925 right here, with a little bit of penalty in most of the other years. Okay, looks like 28 and 29 were really good, no penalty, but 1925 is a problem. If I look at the data right here, this shows me that, yeah, so it's all in the slack variable, not the surplus. So that tells me that we're violating the minimum constraint. Okay, off camera, I modified this part B from TRES1 to TRES1 min. Same values, but now what I want to do is create a T1 res max. So if you're familiar with DSS math functions, you can just add 5. So add and 5, and then click on compute, and then file save as. And the only thing I want to change here is part B. I'm going to call it max instead of min. Okay, and then click OK. All right, so we should have a maximum and a minimum in the actual reservoir storage right here. So let's go ahead and highlight all three and then click on the table. Just kidding, I'd rather look at the plot first. Here's the plot. I'm going to zoom in just on the first few years here. It makes it a little bit easier to see. Now, yellow is the minimum storage based on the minimum guide curve we just arbitrarily created. Red is the maximum, and then green right here, this is the actual storage. So wherever green is below yellow or above red, that's where we have a problem. That's where we're going to have a violation. Let me make this a little bit wider here. Here's the green. Okay, it looks like we're doing pretty good. Looks like there's a little violation right here in water year 1923, and then 24, and then 25 right here. This, I believe, is the worst violation because, again, yellow is minimum, and then the green is the actual storage. And then, again, just to quantify the errors by looking at the slack and surplus variables, what we want to do is eliminate any non-zero values from this plot right here. And what I propose we do is to encourage the water in the reservoir to equal the maximum because there's no penalty with releasing extra water, but there is penalty with not meeting the demand. Therefore, we can play it safe and incentivize this green line, the storage of the water in the reservoir, to be at the maximum value. All right, so to do that, let's go ahead and return to our files and then go to, let's see, the objectives right here. I'm going to add another objective, and boom, here it is. This is encouraging the water in the reservoir to be as large as possible. Now, the incentive value right here, the coefficient is only 1, which I purposefully made less than the violation of 5. Or actually, it's this 5 down here, the penalty with regard to exceeding the maximum value for that moving storage guide curve. So that's the only change I'm going to make. Let's go ahead and run the model again and see what happens. Right click and then run as. Let's go back to our results. I'll click on view, refresh catalog, and then let's take a look at the slack and surplus variables first. And beautiful. So this is what I'm going for. The values are right down here at 0, which means there's no violation in the maximum or minimum, what I'm calling guide curve range. Let's take a look at how the actual storage compares to its minimum and maximum range. All right, so let's zoom in once again. It's kind of hard to tell here. All right, cool. So yellow is minimum again, and then red is maximum. And then here in green, if you don't know your colors, this is green. The green is on top of the red line as much as possible, it looks like. You can tell it's definitely staying above the yellow line. Let's scroll over to our critical year right here, 1925. Okay, and then again, here's the green. This is green. And it looks like we actually were smart about staying at the upper limit of that guide curve because we have less inflow and higher demands, I assume, at the first half of 1925. But we satisfied that minimum requirement and the maximum requirement, as well as the downstream flow requirements. And that's all I had for this exercise where we built a reservoir and we created a guide curve, a single value, and then multiple different values per month. And then finally, we created sort of a guide curve range here with a minimum and a maximum, and still was able to satisfy the downstream flow requirements despite not getting a lot of inflow here in our critical year of 1925.